On Wednesday, there will be the midterm. So what did we did last time, right? We have a lot of math, right? Some of them actually I did not use efficient approach. Like said after the class, he told me that some of them can be simplified. But anyway, our goal was this. We studied the behavior of a qubit under the external magnetic field with B0 pointing in the Z direction, right? And then we have a rotating magnetic field, treated as a vector, right? It is a vector, rotating on the XY plane. And because of this, we can model the magnetic field as B perpendicular, which is a vector, right, equals to just the magnitude, right, maximum magnitude, cosine omega 1 t plus phi on the x direction, plus sine omega 1 t plus phi in the y direction. Is that okay? This is just representing how the magnetic field is rotating, right? And it's rotating at an angular velocity, angular frequency of omega 1. Okay? This is omega 1. Okay? And we use the Hamiltonian we have learned. The total Hamiltonian is just negative the magnetic moment dot the magnetic field, right? And magnetic moment, again, is just the gyromagnetic ratio times the spin vector, right? And if you do this, then you will get this expression. And actually, I don't need to write this because we are not really doing any perturbation. The whole solution is full. Yeah, there's no approximation, right? The most important thing that we have learned is that we try to look at the rotating frame. It means that we try to follow the magnetic field, the horizontal magnetic field when it is rotating, right? So by doing this, we are able to come up with a new Hamiltonian, which is time independent. And now you see that it does not depend on the time. And particularly, it has three terms. One is related to sigma z. One is sigma x, another is sigma y. The sigma z term, it has a delta. Delta is the so-called detuning, right? And delta should be equal to omega 1 minus omega L. Let me check if that is correct. Do you remember? Yeah, omega 1 minus omega L. Omega 1 is the angular frequency of this magnetic field, right? And what is omega L? Do you remember? What is this? Yeah, I mean, Lamarck precession frequency, right? Very good. So he even say that this is equal to E over M B0. But more accurately, it should be gamma B0, absolute value of gamma, right? Because it's electron, I assume the G is approximately equal to -2. Right? This is -2 something, right? So because gamma is actually G divided by 2, E divided by M. Okay, so you don't need to, I mean, you can put in cheat sheet, right? This thing, you need a long time to really memorize it, but whenever you see E over M, it's like gamma, right? So this is the detuning. So basically, it's saying that if I'm actually when the rotation of the magnetic field is at the same speed as the Lamarck frequency, I actually do not have any Z component, which makes sense, right? Because you are just going along this precession. Of course, you don't see precession. Just like you're rotating with the Earth, you never feel the Earth is rotating, right? Unless you're rotating faster or slower than Earth, then you see the Earth is rotating, right? And you also have these two components. But here tell us something, right? Now we have gone through so many exercises. The easier thing, the simplest thing is that under a magnetic field in the z direction, we know that it's going to have the Hamiltonian of what is that? H bar divided by 2 omega L B0, right? If you only have this Hamiltonian, times sigma c. If I don't think about the, is this right? No, sorry. There should be no B0, should be sigma c. Right? So when you have this more precision, right? Basically, this is the Hamiltonian, H bar divided by 2 omega L B0. Basically, just say if you have a magnetic field, the Hamiltonian is just like the precession frequency you have, right? And then times that vector. So you can imagine if we generalize it, every of this term is just like this. We have some angular frequency that's rotating, right? Here I have omega R, which turned out to be the rapid frequency. The rapid frequency in this case turns out to be B perpendicular times gamma, right? This is B perpendicular times gamma. But anyway, this one let us try to simplify it as something H bar divided by 2, an angular frequency, which is a vector. Now, rotation, actually, angular frequency can be a vector because it has direction, right? For example, if you have a plate that is rotating with omega, and if this is the axis, right, then it actually has an angular frequency, which is a vector, right? If you rotate it by 90 degree, 45 degree, then even if rotating at the same frequency, is angular frequency will be different from the previous one because the direction is different. So basically here is telling us that, hey, this one also can be written as H bar omega vector dot product with the Pauli vector, right? So what is this angular frequency? It is this one. It's just omega L cosine phi, omega L sine phi, and then negative delta. And then, of course, the Pauli vector is sigma x, sigma y, sigma c. Okay, so in summary, yes, we went through a lot of math. Those skills I would like you to be able to master, maybe not for the exam, but those are something that you will see pretty often in this area. It's good to know how to deal with those math. But after all, the main point is that you come up with a very simple Hamiltonian for this system. Just H bar divided by 2 omega dot sigma. Like here, H bar divided by 2 omega L sigma z. This one is so simple. But now you just make everything as a vector, right? And this vector has some special component. It's determined by the rapid frequency, which is the magnetic field, and also the initial phase of your magnetic field. Right, so this type of form you will see very often in the future, including the superconducting qubit. It's just that at that time, this component becomes the so-called charging energy of the Josephson junction or whatever. But it has a very similar form. Okay, any questions? So from here, then we will try to spend just a little bit time to understand what this equation is about. So I just rewrite the Hamiltonian that we have got, right, in the rotating frame is negative H bar divided by 2 delta sigma z plus H bar omega R divided by 2 cosine phi sigma x and then plus sine phi sigma y, right? Which is equal to H bar divided by 2 omega dot sigma. okay, with, okay, let's finish this. Omega equal to omega r cosine phi, omega r sine phi, and then negative delta. Yeah, question?
Can you remind us what omega r is?
Yeah, omega r is the effective, it's the rapid frequency due to this perpendicular electric field. So omega r was defined as the gyromagnetic ratio times B perpendicular. Right? You forgot Larmor frequency is just equals to the gyromagnetic ratio times B0, right? Where this is E over M, if you simplify it. Very good, right? So this one actually determines the rapid frequency. In this case, remember before when we do the sinusoidal magnetic field in x direction, it should be gamma times B1 divided by 2, because that was sinusoidal in one direction. And we showed by rotating wave approximation, effectively, it only has B1 divided by 2 magnetic field. Right here, it turned out to have B perpendicular. Is this okay? Any questions? I want to make sure all you can follow. Do not just go home and then study again. That's a waste of your time. Okay, these are equations, but let's understand a little bit better what these are. What if the delta equals to 0? What does it mean? It means I set the rotation of my xy plane electric field omega 1 equal to omega L, right? Right? Basically, I'm saying that, remember what is omega L? This is omega L, and omega 1 is just what is given, right? So basically, I rotate it. Then it's very normal because the qubit is going to precess about the z-axis due to B0. And when it is precessing, I'm trying to rotate by following that frame. Then I'm not going to see myself rotating, right? So what will happen to this one? Then let's try to draw this. This is C, this is X, this is Y, right? So when delta equal to 0, what is omega? Then when delta equal to 0, omega equals to omega K cosine phi, omega, not K, sorry, omega R, right? I also make it difficult for myself to read because this is the rapid frequency, right? Omega R, psi phi, and 0. This is a vector, right? So where is this vector? The vector must be on the xy plane, right? So maybe one of them, maybe here. This is omega. Okay? So this is omega, right? And if I have a qubit, then it is going to rotate about this omega. For example, my qubit may be here, right? And then it's going to rotate as a cone, right? And I think it's going to rotate by right-hand rule. Okay? It's just like when the omega is in the z direction, then you will just precess about the z direction. But in this rotating frame, right, only in this rotating frame, then it's going to rotate about this omega. Right? So let's look at another case. For example, what if, how do I do this, right? This is one case, right? And there's another case, we still have this delta equal to 0. But let's say, let's make the phi equals to 0, then what does it mean? It means this omega is equals to omega r 0, 0, because sine phi equals to 0. Okay, so basically, now, if I look at my omega, it is just in this direction only. This is omega vector, right? Again, we are in the rotating frame. Then if you have a qubit, for example, here, then it's going to rotate about this 9. I don't know if you can see that. Maybe I should redraw it with a smaller circle. Like I have a qubit. This is the Bloch sphere, right? Again, you will go over the right-hand rule, right? So it's going to rotate about this omega, right? And what if you are on the top? You will go down from the North Pole to the South Pole, right? So that's why this is the rapid frequency. But this is on the rotating frame. Now, if we go back to the left frame, what will you get? This is rotating frame, right? If you go back to the left frame, what will you get? The difference between the rotating frame and the left frame is just that I am rotating at the Larmor precession frequency, right? So in reality, right, it's a little bit difficult to see, but because I start from here, so you will be actually not just going down, you will just precessing down like this. Is this okay? While in the rotating frame, you just see that it's rotating about the x-axis, but the left frame is actually precessing downward. This is just very much like the rapid oscillation we saw for the linear magnetic field. Right? Yeah.
Professor, for the first two, is it spiraling or is it like just rotating on this?
Just rotating on one circle. Oh, the cone I just to guide your visualization so that you see that this is the axis of rotation. Yeah. So this plane plus this axis will form this cone. Yeah. It's a good point. Yeah. It's only on this bottom, the base of the cone, that it is rotating. Right? Doesn't look very useful yet, but it will be useful later when now you start seeing that, or how this Hamiltonian is related to the rotation on the Bloch sphere. Yeah.
Is the oscillating entirely? Like, if we started at the same point you have in the rotating frame, is it going to go in the lab frame? Is it going to go all the way down to the pole? And
no. What I mean is, it should be confined to the same height.
Okay.
Yeah. Then you will go back. Yeah. Good point. Right? Just imagine it's just like on the merry-go-round, right? I'm only jumping in this angle, right? So now you look at the left frame, the ground, right? Someone watching me. I will be also just jumping at this band, yeah, within this band. Good point, yeah. Yeah.
Are these two same, similar?
Which two? Huh? These two? Yeah, rotating frame is just saying that I am actually following the Larmor. I'm following the omega 1. Right, so I actually don't see the rotation about the z-axis. This is like I go back to the lab. I have precession and also this rapid oscillation at the same time. Okay, the drawing, actually, I'm not sure if this is exactly, yeah, this should be correct, yeah. Because when you are going down, then this is also moving around, so you will gradually slide down, right? Okay. Yeah.
Is that lab frame in a single dimension?
Left thing is what?
Is it a
It's still 3-dimension. It's still talking about the Bloch sphere. But left frame, the rotating frame, remember what we said is that we try to convert our Hamiltonian to rotating frame, means that we follow the rotation of this magnetic field. So I do not see a magnetic field rotating. I only feel a constant magnetic field actually, because I'm rotating with the magnetic field, right? And that also can explain why, because now you're constant. Isn't that, it's just like the constant magnetic field, I will just precess about this magnetic field, just like what we learned in the z direction, right? Okay. Another example, right? So maybe I just summarize it here. So when delta, no, I still have the delta equal to 0, and I say this already, if you have phi equal to 0, right, your Hamiltonian is just equals to h bar omega r divided by 2 sigma x. Maybe you cannot follow. Think about this. Hamiltonian is still h bar divided by omega dot sigma, right? But now it's omega r 0, 0. So when you do the dot product, then this term is gone. This term is gone, right? So you have omega, h bar omega r2, and then sigma, h bar omega r2 sigma, right? And you can also try to have the initial phase being different. This is very similar to the superconducting qubit. You also control the qubit when you apply a pulse to it with different starting phase. Here is the magnetic field only, right? This is like more like NMR, but this is the concept is the same. That's why we spend time to understand this, although we don't fully understand yet. Then the Hamiltonian become h bar omega r divided by 2 sigma y. Basically, you see that I just changed the phase. I can effectively do the rotation about the y-axis or about the x-axis, right? So here you see how they control the qubit, right? Now, what if delta is not 0? If delta is not 0, then of course the omega is going to be not along the plane. For example, let's say I just give the full solution, right? Negative delta. It's no longer 0. Then if you draw on the Bloch sphere, right, this is Z, this is Y, this is X, right? And now see what color did I use? Should be the red one, but anyway. Instead of the XYZ plane, what do you get? You will get something going down, right? So this is a little bit difficult to see, but you will see it has a Z component. Right, which is negative delta, right? And it also has XY components. That is pointing down, right? So if you do the rotation, you will be rotating I don't know how to draw it. Maybe along here, right? And then the cone, of course, going back to the origin, right? And just have this idea first, right? So we basically done the math treatment for the silicon qubit. We almost done, except we have not talked about the 2 qubit gates, which I'm going to discuss later. Okay? Any questions? Yeah.
Are we missing something? The delta term, yeah, 90 degrees or something, like pointing straight down or straight up.
No, it is, okay, so here I have not introduced, you do have by the way, so this one is not going to oscillate at rapid frequency. I forgot, general rapid frequency, it will be going to oscillate at the magnitude of this one is going to be R squared plus delta square root. The frequency is not the rapid frequency. I mean, the omega R. Just for your information, it will be longer. Now he's saying that are we missing any terms? So that how can we get to vertical? So in this case, no, we are not missing. It's just that you need to make delta much longer than omega R. Okay, but what is omega R? Omega is B perpendicular times the gyromagnetic ratio, right? So you can make that term very small, and then just have enough detuning, then you can go to that one, yeah. But that is the limitation of this one. Okay, so let's